All right, so now let's look at a couple of examples that the explanatory variable in the model comes as a squared version or quadratic version, or I don't know, cube version, and etc. So in terms of motivation, we have a clear understanding of what's going on and why we need to do something like this. So let's go over this example. We are regressing consumption on income, right? Let me actually pull up my whiteboard. So imagine this is a data set for consumption versus income. So we know that if income increase, consumption increase, right? And however, let's say we look at the data set and it's like this. Clearly, if your income is increasing, your consumption is increasing, but in an increasing rate. So we have increasing return to scale, right? In simple regression model, we said that we cannot do anything but transform, for instance, consumption to log consumption and then do the model, right? Here, we're going to say that because it's, now we have multiple regression model, I can put a squared version of inc in the model as well, and then see what's going on, and then look at the fitted line, right? So this fit, how can I get this fitted line there? By doing this regression. Regressing consumption on beta 0, beta 1, income plus beta 2, income squared. Plus, I don't know, a bunch of other explanatory or other unobservable factors. We call them error, right? So this is very good, right? This is very good news because without doing log transformation, by incorporating this squared version of income in the model, we are able to capture something like this, which is absolutely is going to be a better fit than this, right? So which one is a better fit? So let me actually show you the green one. The green one is this: consumption is equal beta 0 plus beta 1 income. If I ask you which one is a better fit to the model, to the data, well, obviously the answer is a red curve, right? And this is a red curve. And multiple regression model allows us to do that. Allows us for having more flexible functional form. So that's what we mean. Okay. So far so good, right? However, when it comes to the interpretation of what's the effect of because the income on consumption, at the end of the day, what are we doing all these things? Because we are interested to see what is the effect of income, our independent variable, on consumption, right? Dependent variable. Okay. So if it was simple regression model, that was easy. How did you say that? So for instance, you say, okay, the effect of income on consumption is going to be beta 1. All right, holding everything else constant, we simply assume that error terms are irrelevant, right? Basically, we said that, okay, if income increased by some units, then the consumption is going to increase or decrease by beta 1, right? What about here? What about this model? Am I able to say something like that? Am I able to say that, okay, beta 1 is equal to changes in consumption divided by changes in income? The answer is no. Because remember, what are we doing here? I think that now's the right time that I can talk about derivatives to you guys, and hopefully you have an understanding what is derivative, right? So here in this green model, the simple regression model, if I take derivative of this formula with respect to income, right? So if I take the derivative of consumption with respect to income, what do I get? Now here's linear, so the answer is going to be beta 1. And these are equivalents, right? Derivative and changes, if the changes are small enough, they're exactly equal to each other, right? So basically, in simple regression model, we were taking derivatives to see what is the effect of income on consumption, what is the effect of x on y. Literally, we were taking derivative, but we didn't call it derivative because we just wanted to keep things simple. But now in multiple regression model, it's time to come up with a more exact and accurate explanation. So basically, we have to take derivative and then start interpreting things. This means that if I'm curious, again, in multiple regression model, if I'm curious what is the effect of income on consumption, I have to take derivative. Take derivative of consumption, basically derivative of this formula with respect to income, right? And now I want you to focus on this formula and tell me what is the derivative with respect to income. So if I want to take derivative, I have to go over the formula, and wherever I see income, basically literally take the derivative. So I have beta 1 income. So what's the derivative of beta 1 income? So the answer is beta 1 plus beta 2 income squared. What's the derivative of beta 2 income squared? 2 beta 2 income. Does that make sense? So it's not going to be beta 1 anymore. The new model, the derivative is beta 1 plus 2 beta 2 income. What does this mean? Again, intuition is very straightforward. It's telling you that the effect of income, so I want you to pay very good attention because it is important. The effect of income on consumption is a function of income itself. What does it mean? So it says that, and if this number is positive, so what does it imply? It says that for higher levels of income, the effect of change of income on consumption is higher. Does that make sense? For lower level of income, the effect of income on consumption is lower. For higher level of income, the effect of income on consumption is higher, because literally there is this effect of income on consumption is a function of income. So in this example, let's say it's an increasing function of income. Let me show it on the plot. So we're saying that, so again, remember guys, what is derivative? That's a slope. So in the green line, what's the derivative of consumption versus income? Slope. We call them beta 1. Here, look at that. Is the slope constant? No. As income is increasing, what will happen? What is happening to slope? Slope is also increasing. So our interpretation is changing for different level of income, right? So we have to say that, okay, if income increase, the consumption is going to increase, but at an increasing rate. So this is very important. And when it comes to quantify these numbers, we're going to see that, for instance, we'll see some numbers. Later on, we're going to use R, and we interpret these things. We simply need to plug those numbers here. So I have a number for beta hat 1, number for beta hat 2, and then to just plug it here and say if income is, for instance, 0, that's the number. If income is 0, that's the number. If his income is 10, that's the number. If income is 20, that's the number, and etc. And we're getting, in this example, we're getting larger and larger numbers as we increase the income level. Okay, now let's go back to the slide. So this is the model, regressing consumption on income and income square. Now we know why we need to do something like this, because we look at the data and the data suggests that. And so model has, however, be careful about these bullet points. The model has 2 explanatory variables. Don't get confused, guys. Do not say that we only have our explanatory variables income. No, it is income and income square. We have 2 explanatory variables. So here in this example, k is equal to 2. This is one variable, this is another variable. Okay, income and income square. So that's multiple regression model. It's not simple regression model. 2, consumption is explained as a quadratic function of income. Okay, again, we believe that this is the idea. 3, one has to be very careful when it comes to interpretation, and we talked about this interpretation. Where is this approximation coming from? Because we know that this is the derivative. These are changes, and changes and derivatives are very close to each other, if the delta is small enough, right? So by how much does the consumption increase if income is increased by 1 unit? That's the answer. The consumption is going to increase by beta 1 plus 2 beta 2 income if income increased by 1 unit. Then we have to say, okay, income from what to what? From 10 to 11, from 100 to 101, and etc. And so here in this example, we say that, so for instance, let's put some numbers into it. If income increased from, let's say these are our family income, $1,000, let's say from 10,000 to 11,000 versus 100,000 to 101,000. In either case, you're changing income by $1,000, right? But the consumption is going to increase a lot more for the latter, when income increased from 100,000 to 101. Okay, so that's the idea. So again, be careful, the interpretation changes dramatically. So here's one example. Another example is this one. Actually, here we're incorporating log transformation and quadratic version at the same time. Nothing, because now you have multiple regression model, nothing can stop you from making the model as flexible as possible, right? So for instance, I think, do you remember this model, this very naive basic model that we actually look at this one in the sample exam? We were regressing salary on sales. So this was our simple regression model. And now we can easily go beyond this. Do you remember that at the very first class I said that, okay, we're going to start everything by simple regression model, but when it comes to real world application, there's literally zero chance that you use simple regression model because, you can have a lot more flexible models, Why do we need more flexible models? Because you want to come up with better predictions, right? But at the same time, we should be very careful, it comes with a cost. If you make your model super flexible, it's a separate discussion, but we say that, okay, maybe the model is going to overfit the data, okay? Yes, it's going to work very good in the sample, but out of the sample, it's not going to work properly. But again, that's a separate idea. However, in multiple regression model, let's make it at least a little more flexible, not just this plain model. We're going to make it a little more flexible. Let's go, instead of working with salary, let's work with log salary. Instead of working with sales, like work with log sales. And you know what? I want to incorporate some other exponential variable. So this CEO10, this is a we're going to put both of them. This is tenure of the CEO, and we put CEO10, and CEO10 is squared. For some reason, we put the squared version as well. Okay, so here comes the question usually for students, especially when they're at the beginning of exploring the multiple regression model. How do you know that I use log? How do you know that I use quadratic? Why did I not use Q? Why did I not use to the power of 5? The answer, some part of it comes with experience. If you're working in a field for, I don't know, many years, you can see what is the relationship between variables, so you have some prior belief. So that's the straightforward answer. But you want to say that, okay, I have no idea what does this industry look like. I have zero background, but I'm gonna put many different versions of the models. I want to put CEO10, CEO10 to the power of 2, to the power of 3, to the power of 4, log CEO, and etc. And at the end of the day, the data suggests me which one was relevant, which one was not. So don't worry too much that, okay, how did I know that put this one and this one? You don't know. Again, if you haven't worked in that industry, if you're not familiar with the data, you don't know, that's totally fine. You just put it there and then see what the data is suggesting, right? And this is, guys, this is actually what you're going to do for your final project. So for your final project, you have a research question, and I will ask you specifically incorporate different functional forms. And usually students come up with 10, 15 different models, and then explore them and see at the end of the day, one of them worked best, and try to present the best model. Okay, so this is what we do here. So in this example, so this model, for instance, is assuming constant elasticity relationship between CEO salary and sales. Remember, this is log. Between salary and sales, this is log. And it assumes quadratic relationship between salary and CEO10, the tenure of the CEO. Remember, the model has to be linear in parameters, not in variables. This is perfectly fine. We're not violating assumption number 1. So the coefficients, if you look at the, if you look at the coefficients, they are not nonlinear. They are linear. So that's perfectly fine. All right. So we talked about this one. So the rest of it is pretty straightforward. We can, because again, we know what is simple regression. How does simple regression model look like? We can easily move from simple to multiple. So random samples. These are all less estimation of the regression model. So basically, we're saying that how we do that. Remember, in 2 dimensions, when we deal with simple regression model, y versus x, we said this is the data, and the model is doing something like this by scoring these residuals, summing them, adding them together and minimize that equation, here is exactly the same. So the difference is that instead of one line, no, 2 dimensions, we have 3 dimensions. So we have x1, x2. Again, if I have only 2 variables, it's 3 dimensions. If I have 3 variables, it's 4 dimensions, and etc. Right? But we can only visualize 3 dimensions. So so we're not going to come up with a fitted line. We're going to deal with a fitted plane. So let me actually pull up a visualization. Well, I'm gonna do it when I switch to computer, because I have to show it in R to you guys. But for now, just remember that at the end of the day, a multiple regression model, again, if it is 3 dimensions, 2 exponential variables, you're doing something like this. It's a plane. It's a hyperplane. It's not a line anymore. Okay, but the idea is exactly the same. So you are minimizing the residuals from this hyperplane in 3 dimensions. So we're doing exactly the same thing. The residual is defined exactly as before, yi minus y hat I. This is your y hat. And we're minimizing this optimization. So this is our optimization. We are minimizing the solve square residual. Exactly the same. Okay. Now we use the data, use OLS. OLS will give back beta hat 0, beta hat 1, beta hat 2, and etc. Okay. And then we can interpret them. Okay. And of course, this minimization will be carried out by computer. Okay. For simple regression model, we could do it manually, but for multiple regression model, it doesn't make sense to do it manually. Either way, we used R to calculate these numbers for us. Algebraic properties are going to be exactly the same. Well, this is just terminology again. The same things, fitted values and residuals. These are the fitted values or predictions. These are the residuals, y minus y hat. And again, algebraic properties are exactly the same. The summation of these residuals is 0. The correlation of residual with all the exponential variables is 0. And the averages lie on the regression fit. So it's not line anymore. If it is 3 dimension, it's a hyperplane. If it is 4 dimension, I have no idea what it is, right? So a human eye cannot have a good understanding of more than 3 dimensions, right? But it is something, right? But we know that the averages will lie on that something. Okay, application in R, as always, this is a good news part, cannot be simpler than that. We can literally do it in a couple of lines. So, in chapter 2, you guys tend to use a stargazer, but in chapter 3 and 4, etc., sometimes you would be better off using the summary output. Sometimes you would be better off to use stargazer output. Okay. So for documentation, usually I personally prefer to work with this one because it looks a lot better. It's a table. It looks better. However, when you want to read, for instance, the t-values and etc., it's just the output of the summary is better. But let's look at an example. So we are regressing wage on education experience. So 2 variables. See, wage, LM wage tilde education plus experience, then data frame. That's simple, right? That's it. That's all. So this is your regression. You can either call a summary function of it or call the stargazer function. So if you do summary, this is the output. You're already familiar with the output. So for instance, this is your beta hat 0, beta hat 1, beta hat 2, and you have the standard errors. Do you remember those ugly formulas for simple regression model? For multiple regression, it's even uglier than that. But again, the good news is that we don't need to calculate them manually. And we can look at the t-values. T-values and p-values are something new that we're going to explore later on. But again, if you want to explicitly look at the t-values and p-values, the summary output is a better one. If you want to look at, just some nice table, but without explicitly telling you what is t, what is p-value, use the other table. Okay. So again, education. This is our beta hat 1, beta hat 2, and beta hat 0. And what else do we have? We have number of observations, R square, adjusted R square. This is something that we finally are going to talk about in this chapter. And let's talk about degree of freedom. Actually, this is cool. So let's say the observation is 526. 526 is my n. What is the degree of freedom of the model? Do you remember we talked about this? N minus k minus 1. Okay, so n is 526. What is k here? How many explanatory variable do I have? And don't get confused here. K is the number of explanatory variable, not the intercept. Okay, so the k is equal to 2. So it's 526 minus 2 minus 1. So what do we get? 523. Do I see this one somewhere? Yes, this is our 523. The degree of freedom of the model. All right. So I'm going to make a very short, quick video on the application in R. Basically, I'm going to do all these things that we just saw in R, and then show you that graphic, visual representation of the 3D things of the multiple regression model. All right, see you in the next one.